In this video, we will discuss the derivatives of trigonometric functions. Our learning objectives are fairly straightforward. Number one, know how to use and use the formulas for the derivative of our 6 different trigonometric functions. And then we'll want to combine previous derivative formulas with trig formulas as well. Take a moment, pause the video, write down your 6 different trig functions because we will use these as the foundation for all our work. I'll note we're not going to prove these in this video. The proofs will actually be in another video on our channel. Also, there are these 2 special limits that we will use and prove in the other video. We'll use them in this video. We'll prove them in the other. You'll note these are 2 limits that we already examined earlier in the year, but we did a geometric understanding. We used basically some intuition to say that these were true. We'll go through and prove them in our other video. Ultimately, this is what we're looking at doing. We have a function like y equals x cubed times cosine x. Differentiate it. So this is telling us if we take the derivative of y on both sides, how do we do it? Well, first off, d dx of y is dy dx. And on the right-hand side, we're going to note, since we have a product, we must use the product rule. So f is our first function. That's x cubed. Then we have to multiply by the derivative of cosine of x. Add our function g, multiplied by the derivative of the first function. Well, x cubed we have. What is the derivative of cosine? We can look back at our table and note the derivative of cosine equals negative sine. So just applying the formula, we'd get negative sine of x. On the right-hand side, we have cosine multiplied by the derivative of x cubed. According to the power rule, we get 3x squared, and we're done. This is our derivative. If we'd like, we could rewrite it, we could factor it, we could do a bunch of different pieces with it, but this piece is finished. Our second example, we have y equals cotangent of x over 1 plus sine x. You'll note that since this is a quotient, to take the derivative, we will need to use the quotient rule. Okay, so writing it up, dy dx, according to the quotient rule, is the denominator function multiplied by the derivative of the numerator. Subtract the numerator, multiplied by the derivative of the denominator. And that will be all over the denominator squared. Okay, so bringing this down, our dy dx is equal to, we still have 1 plus sine of x, and we need to take the derivative of cotangent. Once again, we can scroll back over, take a look at our tables, and say the derivative of cotangent equals negative cosecant squared. So we get negative cosecant squared of x. Subtract cotangent multiplied by the derivative of 1 plus sine of x. Derivative of 1 is the constant 0. Derivative of sine equals, coming back over to our table, the derivative of sine equals cosine. So we would get cosine of x all over 1 plus sine of x quantity squared. And with that, we are done. We actually do have a formula for the derivative dy dx. We could continue further, though. In a lot of instances when you're working with trig functions, you could use some algebra to rewrite it, to simplify it. I would like to continue this by trying that out. Frequently, a valuable tool is to rewrite them all in terms of sine and cosine. That's not always the case, but frequently it is. You would have negative 1 over sine squared. Cotangent is cosine over sine, so we'd have cosine squared over sine. Didn't want the squared part just yet. Cosine over sine times cosine. And looking at these pieces then, we could note we'd have 1 plus sine of x quantity squared. That these are a lot of pieces that we could start expanding. If we started to use the distributive property, we'd have 1 times negative 1. So, and I'm going to scroll this down more to give me more room to work. Okay, we would have negative 1 over sine squared x. Sine times negative 1 over sine squared would be negative 1 over sine of x. Then we would have minus cosine of x, but it's not just cosine, it's cosine times cosine, so it's cosine squared. Why did I write the 2 there? That was silly. Cosine squared x over sine of x. Okay, so you notice how we have the negative 1, and minus. If we factored out that negative, we could actually say this is a negative. This would be a positive, and both of the negatives factored out as well. And we could note this one further by recognizing with our denominators in the, with the sine denominators in the overall numerator, we could rewrite this one as sine of x over sine squared. Then we'd have cosine times sine over sine squared. And combining them this way would allow us to simplify this by saying we have cosine squared x times sine of x plus the sine of x minus or plus 1. And that's the whole thing, because we had that whole piece when we factored out the negative. But this is all over sine squared x, all over 1 plus sine of x quantity squared. You may recall, if we have something of the form a over b all over c, this could actually be rewritten as just a single fraction. I'm going to use that algebraic rule to complete this part, which would allow us to rewrite this as negative cosine squared x times sine of x plus the sine of x plus 1 all over sine squared x times 1 plus sine of x quantity squared. And so with this last part, we are finished. We should note, took some algebra, yes. Does it really look that much better to what we had here in the black? Maybe, maybe not. It depends on kind of your preference. If you like these ones that are all in terms of sine and cosine, yeah, maybe it's not so bad. But if you don't mind having the other pieces like cosecant, cotangent, then the original one probably was there. The original one in black was probably better. In large part, it depends on what you're trying to do with it. If you want sines and cosines, you do it. If you want to try to solve when the derivative is equal to 0, if you want to take another derivative, a lot of times it just depends on what you're trying to do with it. Different strategies wind up playing a role all over the place. Okay, our third example. An object at the end of a vertical spring is stretched 5 centimeters beyond its resting position, and then it's released at a time t equals 0. Please note, though, that when you stretch it downward, 5 centimeters down is our positive, so we're not using the traditional 5 is up, negative 5 is down. We have an inverted coordinate plane in this one because down is positive for this particular problem. Its position at a time t is s equals f of t, is given by the equation 5 times the cosine of t. Find the velocity and the acceleration at a time t. Okay, well, how do you get velocity? We know the velocity is the first derivative. So what is the derivative of 5 times cosine? Well, we'll go back again and say the derivative of cosine equals negative sine. And so we're getting this piece of negative 5 times the sine of t. Then we want the acceleration. Remember, acceleration is the second derivative. So we'd have to take the derivative of negative 5 sine t. The derivative of sine equals cosine, so we'd get negative 5 times cosine of t for our acceleration function. So just some quick analysis. I'm not going to go too in-depth with it. What does the velocity mean? Well, remember that sine is governed between, or is bounded between positive and negative 1. So since sine has to oscillate back and forth between negative 1 and positive 1, it tells us that this piece is going to bounce back and forth between negative 5 and negative 5 times positive 1, so 5 or negative 5. Our velocity is oscillating back and forth between a speed of 5 and a speed of negative 5 centimeters per second. Which should make sense, because if our velocity is positive, it's telling us this thing is bouncing down. If our velocity is negative, it's telling us it's bouncing back up. And when you take a spring and pull the weight on it, we know it acts like the rubber band, like springs do, and they tend to bounce back and forth for a while until they tend to return to their natural state. We have the same issue with the velocity, or the acceleration function. Cosine is also governed between positive 5. Cosine is bounded between negative 1 and positive 1. which we run into the same issue that our acceleration will go between -5 centimeters per second squared and +5 centimeters per second squared, which is telling us that it's oscillating backwards and forwards between slowing down, and speeding up. If we have a positive acceleration, like a +3, a +5, a +1, it's telling us the speed of the object is increasing. If we have a negative acceleration, it's telling us that the velocity is slowing down, which again should make sense, because if you pull this weight really far down and let go, it's going to rapidly spring back up until a certain point where it's reaching back at the surface, or back up to its original point where it compresses the spring, and then it slows down, changes its velocity, and because gravity is pulling it back downward, it will rapidly fall until it stretches the spring and slows down, and then bounce back up. It fits in line with what we would expect would happen by stretching and releasing a spring. Here, find the 45th derivative of sine of x. So yeah, 45 derivatives. So we have f of x, which we will note is the 0th derivative. That's sine of x. F prime, the 1st derivative. The derivative of sine equals cosine. The 2nd derivative. Derivative of cosine equals negative sine. 3rd derivative, we'd get the negative derivative of sine, which is cosine. The 4th derivative, well, we're not going to just keep using prime forever. Once you get to the 4th derivative, you use this parenthesis notation with the actual number. And then we would note we'd have the negative derivative of cosine, which is negative sine. But negative sine, or the opposite of negative sine, is simply positive sine. And you should note that puts us right back to our original function. Well, if we repeated this process, we would get the 8th derivative is also sine of x, and then the 12th derivative is also sine of x, and the 16th and 20th. Anything that is a multiple of 4 is going to wind up being the same function. Well, we're noting then that if we kept this process up, we would get the 44th derivative is the original. So if the 44th derivative is sine of x, then the 45th derivative is cosine of x. And we're done. Our 5th example. Find the limit as theta approaches 0 of sine of 4x over 5x. This is a piece that is actually using one of the limits that we mentioned. The important characteristic behind this one is noting theta is matching theta. These pieces are the same, and then again that piece is going down to 0. If we have this situation, sine of a something over something, where it's going to 0, we could just use this theorem and say, overall it's a 1. Again, we'll prove that in the other video. Well, the problem we have here is that we don't have, first off, that's supposed to be as x equals 0. X approaches 0, not theta. I apologize for that. We don't have sine of 4x over 4x. If we had sine of 4x over 4x, we'd be able to apply that theorem instantly and just say 1. Unfortunately, though, it's not 4x in the denominator. It's a 5. So what do we need to do to fix this? Well, the important characteristic that we're noting, we could rewrite that term as a multiplication or as a product of two fractions. The important thing that we need, though, in order to use that theorem, this has to be a 4x. Well, if I'm multiplying by 4x on the bottom, I could multiply by 4x in the numerator, and then you can see how they're adjusting each other. This is a piece that by employing this intermediary term, we could rewrite our limit sine of 4x over 4x multiplied by 4x over 5x, and it's still the same limit. But of course, there are some things that are beneficial to that. We have x over x cancels. So we would get the limit of 4/5 times sine of x over 4x as x is approaching 0. We could factor out the 4/5 using our limit properties, and we'd get limit x approaches 0 sine of 4x over 4x and then we're simply noting that, well, first off, if x is approaching 0, 4 times x is approaching 4 times 0. But of course, 4 times 0 is just a 0. So this part that we have here of x approaching 0 still fits in the idea of saying 4x is approaching 0 at the same time. Well, if we just replaced theta with 4x in this theorem, we could apply that right away and simply say this is 4/5 and the limit is 1. So 4/5 times 1, we get 4/5 for the overall answer, and we are completely finished. Our sixth example, a little bit tougher to see. We are still going to try to take advantage of that same theorem. We know if you have the limit as theta is approaching 0, sine of theta over theta, this is a piece that goes to 1. Before we start launching into this too much, let's try doing a direct substitution. We know that cotangent theta, cotangent is sine over cosine. If we tried to do a direct substitution, we would get 0 squared times the sine of 0 over cosine 0. I'm sorry, I have that backwards. I wrote sine over cosine. Sine over cosine is tangent. I've got to back that part up because I had them reversed. Cotangent is, I want this in red, cotangent is cosine over sine. I wrote those backwards. I don't know what my brain was thinking for a second. So using our direct substitution, we would then get 0 squared times the cosine of 0 over sine of 0, which would be 0 times 1 over 0, which 0 over 0 doesn't make any sense. Direct substitution leads us into something that is not helpful. That's why we want to try to take advantage of a theorem. In particular, the one that I'm going to note is we could split this up. Limit as x approaches 0 of 1 over x times x squared times the cosine of x, 1 over x times sine of x. Now, why am I writing it out this way? The big thing that I'm trying to take advantage of and trying to use, if I have sine of x, I need it to be over an x. So to get this to become the sine of x over x that I need, I'm introducing times 1 over x in the denominator. But because I'm doing that in the denominator, I have to also do it in the numerator. Writing it up this way allows us to then say we'd have the limit x approaches 0 of x times cosine of x all over sine of x over x. So why is this helpful? Because we have a rule that says if you want to take the limit of a quotient, you are allowed to split it up into two limits, but you're only allowed to do this when the limit of your denominator is not, limit of g is not 0. In the original function, if we took the limit, switch the color, if we took the limit as sine of x as x approaches 0, that goes to sine of 0, which is 0. That's why our initial problem wasn't working out well, because the limit of our denominator didn't meet the criteria for our limit rule that we had before. But now we would see that this piece goes to 1. Because it goes to 1, we are actually allowed to split this stuff up into two separate functions, or rather two separate limits. And evaluate the overall result. This one gives us 0 times cosine of 0 over 1. So that would be 0 times 1 over 1, 0 over 1. Our overall result is just 0. This limit equals a 0. And we're completely finished. And here is our last example. Once again, we would like to say, let's just try a direct substitution. 1 minus the tangent of pi over 4 over sine of pi over 4 minus cosine of pi over 4. Well, the tangent of pi over 4 is 1. Sine of pi over 4 is square root of 2 over 2. Cosine is square root of 2 over 2, and when we plug them in, we get 0 over 0, which again makes absolutely no sense whatsoever, so direct substitution fails us again, telling us it's not going to work. Well, what's something that we could try? My first intuition is to say, if we're getting 0 over 0, frequently we're going to have some type of a removable discontinuity. So we're trying to create things that might be able to cancel. And in order to do that, one frequently valid strategy is to conjugate something. If we multiply by the conjugate of our denominator, we will get something that will be in an equivalent form. And if we're lucky, it will locate a removable discontinuity which we could cancel out. So let's do that. I'm going to start with the denominator because it's easy. We'd have sine squared minus cosine squared of x. For our numerator, 1 times sine is sine of x. 1 times cosine is cosine of x. tangent times sine. We'd have minus tangent x sine x. And then tangent times cosine, we'd have minus tangent x cosine x, which on face value isn't very helpful. It gets a little bit better though if we rewrite this in terms of sines and cosines. We would have sine of x plus the cosine of x minus, and tangent is sine over cosine multiplied by sine of x minus sine over cosine times cosine. Okay, so after rewriting that, we can see some pieces that will be beneficial. Multiply by cosine, divide by cosine, cancel each other out. You should then note we have a sine of x with a minus sine of x. Those cancel each other. And that will allow us to rewrite this as cosine of x minus sine squared x over cosine. That's all over sine squared x minus cosine squared x. Hang on a second. Now, in our numerator, we could note that we could get like terms by introducing another cosine, which then allows us to rewrite this whole piece as this format. And I want to center that. That'd be cosine of x. Why is this relevant? Well, we also know further that we could rewrite this as cosine squared x minus sine squared x over sine squared x minus cosine squared x times cosine of x. That's using the same rule that I had before. This plays a role because we should be able to recognize cosine squared minus sine squared. If we change around the order of that so that it was sine squared minus cosine squared, if we change the order, it's the same thing from what we had, but the only difference with it is it's a negative. Looking at it this way, we could then note we have pieces that cancel, finding our removable discontinuity, and so our whole piece then is negative 1 over cosine of x. After all that algebra to simplify, we're eventually able to come back and say, and I'm going to use this purple to kind of separate it. This limit will be equal to the limit as x approaches pi over 4 of negative 1 over cosine of x, which would be the same thing as reciprocal of cosine is secant. Just using direct substitution, this gives us negative secant pi over 4. And the secant of pi over 4 is just the square root of 2. So we have negative square root of 2, and our limit is done. taking all these pieces, coming back. Remember the learning objectives. Know and use formulas for the derivative. Combine your derivative formulas with some trig functions, some trig derivative. Blah. Combine the product rule, quotient rule, limit rule formulas with some of these trig formulas. That way we can calculate derivatives, we can calculate limits, all based on using sine, cosine, tangent, and our other trig functions.